skin tone colours. There isn't any blue colour in human skin. And this computer looks for the blue colour and makes it disappear. And that enables us to cut the babies out with a shape like this, with a nice clean edge, and put them over the clean water frames. The clean water frames are specially shot backgrounds which we use to put in behind all of the babies and all of the shots of Robert to give the impression that he's in a very large pool, or even in the sea, because the pool we were filming in was so tiny.
And this is what we ended up with, a skill babies have that adults can only marvel at.
The truth is, we don't even understand the origins of this remarkable ability. For the moment, at least, it remains a delightful mystery.
Another mystery for me was why I allowed a different team of experts to cover my head in cornflour. They told me it was to make my hair reflective for a scan of my head, enough to make a man turn grey.
One of the things we wanted to do in the series was to link the outside world, the world we can shoot with cameras, normal cameras, and the inside world, which we can shoot with little tiny cameras or which we can image using medical imaging technology. And the best way to do that is to be able to make a seamless journey from that world, from the big world into the tiny world. So we needed to get an image of a person's head into our computer. And there is a way of doing that. It's called cyber scanning. And it's actually a way you make a laser scan, which uses the same kind of laser that you scan your groceries with at the checkout of the supermarket. And it travels around the head and paints a very intricate picture in the computer of the topography, of the contours, if you like, of someone's head. And then that can be folded up to make an image of the face, which we can then manipulate in our computer and journey into.
The cyberscan allowed us to start this amazing sequence, a journey from my head into my ear canal, previously uncharted territory. The fleshy outer ear collects the sounds that surround us and channels them down the ear canal to vibrate the eardrum. On the other side of the drum, these vibrations are transmitted through the middle ear by minute bones. These are the only bones that stop growing soon after birth. An adult has ear bones the same size as a newborn baby. We went even further into the detail of the ear with another imaging technique called scanning electron microscopy. If we zoom right the way in with an electron microscope, we should see something remarkable, the secret of how sound is transmitted to the brain. They're rows of minute hairs only a few thousandths of a millimeter high. As noise vibrates them, they send electrical signals to the brain which we experience as sound.
An SEM, or scanning electron microscope, is a special type of microscope that uses electrons instead of light to look at something. With this microscope we can go to a magnification of about times 300,000, but for most biological specimens about times 50,000 is plenty. At times 50,000 you could see details on the surface of an individual bacterium.
To prepare an SEM, Paul puts the tiny specimen through a complex process of fixing to preserve it. Then he dips it in chemicals to remove all traces of water.
If I was to put the specimen straight into the microscope with it containing water, the vacuum inside the microscope will cause the specimen simply to explode.
It then has to go into a pressure chamber to finish off the dehydration process. Believe it or not, it's then coated in 24-karat gold, which makes it visible in an electron beam.
Once coated, the specimen can be put into the microscope on this special motorized stage. The camera position inside the microscope is fixed, so the only way we can get movement in the sample is to actually move the sample itself. I create the moving sequence using a method called stop frame animation.
Stop frame animation is a painstaking technique, a bit like making cartoons. This is an egg in the fallopian tube. Hundreds of still pictures are taken, each time in a slightly different position, to create movement. A 30-second sequence like this can take surprisingly long to make.
The whole process for a single specimen can take about 3 days from beginning to end to complete.
With SEMs, we've been able to show you some amazing details. Here, the surface of the tongue. And here, hair growing. And different types of hair. Asian hair is circular in cross-section, so it tends to hang straight. Black people have hair which is a flat oval, so it naturally tends to form tight curls. Caucasians or white Europeans have hair halfway between the two, so they tend to have slightly wavy hair. And here, a human egg, and 100 times smaller, human sperm on its surface. Images like this might make conception look easy, but it's not. Kate Hardy is a member of my research team at Hammersmith Hospital in London. For our programme on pregnancy, she filmed a remarkable sequence never seen before on television.
So what we have here is a microscope which enables us to look at the embryo at a high magnification, so we can see what the embryo's doing while it's developing. And round the microscope we've got this perspex box. The embryo can't grow at room temperature. We have to keep it at 37 degrees centigrade, which is the same temperature as the human body. And we find the embryo, focus on it, set the video recorder going so that we have one shot every 2 seconds, and we leave the embryo there for about a week. So this is a very, very nice technique for looking at development over a long period of time and compacting it down to a short period of time so that you can see the changes that are taking place. What you start off with is a fertilised egg, which is a large cell, and this cell will divide about once every day initially. And these cells carry on dividing until there are about 8 or 16 cells about 3 days after the 1 cell stage. And then finally it gets to the stage where it wants to hatch out of the jelly coating that has been protecting it during earlier development, and then it's ready to implant in the lining of the womb. I think the most exciting thing that we've seen so far is the way the cells divide, the speed that it happens over. You get a real feel for the fact that there's a long period of time when nothing happens, and then suddenly you get a cell division, and then another day goes by where nothing happens, and then another cell division. It's amazing watching that on screen.
It's one thing to film an embryo under a microscope. It's quite another to find a way to film the fetus growing in the womb.
The only way you can get into the human body without cutting it open and seeing what's in there is to use an endoscope, which is like a mini telescope, little narrow telescope that you can look through small holes or naturally occurring orifices without having to do any damage to the patient. The endoscopes have a dual system. One is an optical system for getting the image out, and the second is a fibre optic system which allows you to take light in. The amount you get depends therefore on the size of the scope you can use. If you can use a big endoscope, you're looking in something big like the gut. If you're looking into something very small, where you need to use a very narrow scope, then the light problems get worse because everything's small.
Here's another example of how David Barlow used an endoscope in the series. Food doesn't fall from your mouth to your stomach. When your brain tells you to swallow, it triggers waves of muscle contractions. They squeeze things along in your esophagus at around 4 centimeters per second. The first scheduled stop is the stomach. It's essentially a biological liquidizer. Its lining